In this lesson, we're going to talk about slope. So the definition, so the slope of a line is the ratio of the vertical change to the horizontal change. So you've probably heard of this as rise over run. So if you look, it's the change in y's over the change in x's. So if we look at the formula here, so if we have points, well, its slope is equal to the change in y's over the change in x's. It doesn't matter which one you call x1 and x2, as long as you're consistent. So it's just make sure you subtract. If you do second minus the first, then make sure you do the same for the x's. So here's your formula. Shorthand, sometimes we also see this as change in y over change in x. It's another common way to write it. So those are all equivalent. So we can find slope graphically by counting. We can find slope algebraically by using the formula. So we'll look at some examples in a minute, but just to give you a couple reminders on different types of slopes. So when we're going uphill, this is going to be a positive number. So this is a positive slope. If we're going downhill, this is going to be a negative slope. So you should have a negative number as a slope. If it's going horizontal, so straight across, this means that there's no vertical change. This is a zero slope. So this occurs whenever you have 0 on top divided by some number. So it means your change in y's is 0, no vertical change, but there is a horizontal change because that'll 0 divided by anything is 0. So that'll always come out to be 0. This last one is undefined. And this is created whenever you have 0 in the denominator. So this would be something like we have vertical change, but we have no horizontal change. So a number divided by 0 will always give you undefined slope. So let's try some examples. So on the next page here, for this one, since we're on a graph, I want to do this one graphically. So if we're trying to find the slope, graphically you want to think about it as the rise over the run. And I always like to go to the right when I count, so I always go up or down and then to the right. Remember, whatever direction you're counting. So if I'm going up or to the right, that's always a positive number. If you're going down or to the left, these are always negative numbers. So as long as you keep track of your sign, you'll be fine. It doesn't really matter how you count, as long as you always count up or down first and then left or right. So pick any points that are easy to count. So I'm going to just choose this one here. So from here, I have to go up 1, 2, 3, and then over 1. So I'm going up 3 and then over 1. So when I translate that, that's up 3, right 1. This is going to be a positive 3, positive 1, because they're both going towards positive numbers. So I end up with a slope of 3. Now, it doesn't really matter. If I would have said I wanted to choose different points, it wouldn't matter because this is a line. The slope is the same for any equal distance. It's a constant rate of change. So even if I went from here to here, I would have gone up 6 over 2, which would reduce down to 3 as well. If you went backwards, so let's just say I counted the opposite way. So let's say I went from here and I went down 1, 2, 3. So I went down 3. Well, then you have to go left 1. So for me, that feels very unnatural counting that way, but you'll still get the same answer because this is a negative, this is a negative, and then I'll end up with a positive. So again, doesn't matter, just making sure that you're consistent and you're always going up or down first and then left or right. So then the next one is doing this algebraically. So algebraically, without a graph, use the formula. So it's the change in y's over the change in x's. So I write down my formula. It doesn't matter which one you want to call x1, y1, x2, y2. Usually what I do is I'll draw little brackets here to make sure I'm subtracting. So I'll say, okay, I'm subtracting the y's first. So I always usually start right then left. So negative 4 minus 1. And then you want to subtract the x values. So 5 minus negative 2. Simplify that. So we get negative 5 over 7, and then you just leave that. So negative 5 over 7, so this would be going down since it's a negative slope. So algebraically, graphically, the other thing that you might see with slope is parallel versus perpendicular. So how those slopes of those lines relate. So parallel lines are two lines that never cross. So here's an example. Um, their slopes have to be the same because they never cross and they have the same steepness. They're going to always have the same slope. So these will always have the same slope. The y-intercepts will have to be different though, because otherwise it would be the same line. So same slope, different y-intercepts. And like I said, these are two lines that'll never cross. And then for perpendicular, these are lines that cross and form right angles. So something like this. Those are perpendicular. So for these slopes, in order to get perpendicular lines, the slopes have to be negative reciprocals. So slopes are negative reciprocals, which really means that the slopes are flipped and negated. So you flip and negate slopes. So what that means is if I see something like 1/2, flip it, so it'd become 2 over 1. It would be negative 2 over 1 because I'd have to flip it and negate. So negative 2. So these are perpendicular. So you can think of it as negative 2 over 1. Or if I say negative 3/4, that would go with positive 4/3 because you would negate it and become positive, flip it. So those are negative reciprocals. If I have negative 1, well, that's really negative 1 over 1. Flip it, it becomes 1 over 1, positive 1 over 1 because you have to negate it. So those are just some different examples. So definition of perpendicular lines, like I said, so they're two lines that intersect and form right angles. So these, their y-intercepts could be the same. They most likely will be different, but they could be the same because they are allowed to intersect. So if they do have the same y-intercepts, they'll intersect at their y-intercepts. Versus parallel can't have the same y-intercepts. The other thing to point out too, just in case you see it, the symbols for these. So parallel, the symbol for parallel that we use, it looks like almost like a slanted 11. That's the symbol. Perpendicular looks like an upside down T to represent the right angle. So those are the two symbols to represent parallel versus perpendicular when we talk about slopes. And then the last thing to talk about is something called the difference quotient. We're going to do a lot more work with this later on in the next section, in section 1.4. But for right now, difference quotient, average rate of change, all related to slope. So when we talk about the difference quotient, average rate of change, those are when we start expanding outside of lines. But for right now, we're still talking about lines. So if you notice, if you kind of compare this, when we talk about f of b or f of a, that's the same thing as saying y with an input of b and the y value with an input of a. So this is really the same thing if you kind of connect this, the same thing as change in y's over change in x's. It's the same thing. The reason why we call it average rate of change is because when we're talking about a curve, the average rate of change is not going to be consistent for every single interval on the curve versus on a line, the average rate of change is always the same. Um, so that's really the only difference. But if I say find the average rate of change between point P and Q, well, you're really finding the slope of the line that connects them. That's really what you're doing. So we also call this the difference quotient. So what we're going to do is just try this example. And like I said, you're going to see more of this later with the difference quotient and kind of how it plays an important role into calculus. But for right now, I just wanted to practice plugging in. So it says here we want to find f of x sub 2 minus f of x sub 1 all over the change in x's. So what that really means is I have to find two things. I have to find f of x sub 2 and then f of x sub 1. And when I say sub 2, I'm saying x subscript 2 is really the notation. So what I'm going to do is I'm going to basically think of this as I'm going to plug in x sub 2 into this. So I'm going to say this is going to be 3 times x sub 2 minus 5. And then I'm going to do the same thing for this. I'm going to plug in x sub 1 into this function, but notice that there's a subtraction between these, so I have to keep the minus. So I'm kind of using this template, and I'm going to actually keep this in parentheses. Not that we're going to need it for that one, but we will for this one. So now I'm going to plug in x sub 1 into this. So basically, here's the red, here's the blue, and I'm plugging into this function. And then on the bottom, it's just going to stay x2 minus x1 because it's not a function notation. So there's no input that I'm plugging into. This is just going to stay x2 minus x1. So now all I have to do is simplify this. So it's a little bit odd because we replace the red and the blue with using the input and getting the output. So these are the outputs using the x2 and x1 as the inputs. So now we just simplify. So the only thing we really have to worry about is this negative up top. So this is going to end up being 3x sub 2 minus 5 on the top. So I can drop those parentheses minus 3x sub 1 plus 5 all over x2 minus x1. Now we see that these 5's cancel. So I have 3x2 minus 3x1 all over x2 minus x1. Oops, I'm trying to erase this here. There we go. And now what you might be thinking is if I take out a 3 in the top, I see x2 minus x1. So what I'm going to do is I'm going to take the 3 out or factor it out. And then on the bottom, I have x2 minus x1. I keep wanting to make my subtraction sign diagonal. So cross those off. Those divide and end up being 1, so I'm left with just 3. So that's the answer for it. So again, we're going to do more work with it. I wouldn't worry about it too much for right now. You're going to see it a lot more on the upcoming sections.